CDB2 Review: Earth and Space. The continental drift theory proposed by Alfred Wegener in the 1900s that continents drift apart from each other slowly over time was not well accepted because the mechanism or force that moved the continents could not be explained. And that mechanism or force are convection currents in the asthenosphere. Convection currents. So scientists today believe that the driving force of plate tectonics are the convection currents in the mantle. The upper part of the mantle is called the asthenosphere. So what you have here is that you have hot, kind of liquid, more putty material rising because the core is heating it up, and that putty material rises and then it starts to cool off and sink to get heated back up again. And this is what moves our plates on Earth, causing crustal features that we'll be studying about. So Earth plate tectonics. Earth's outer shell, the lithosphere, is divided into a large patchwork of tectonic plates. There are 7 major tectonic plates and many minor plates. There are 3 types of plate boundaries: convergent boundaries, divergent boundaries, and transform boundaries. Let's go over each type of boundary. The first boundary, convergent boundary, the boundary between 2 colliding tectonic plates. The crustal formation depends on the type of plates that are converging. So this is the direction of the plate movement. Think of converging, coming together, or colliding. So if it is a continental plate, which is land and land colliding, what you get are folded mountains. And the elevation of these mountains keep on increasing and increasing. So these mountains get taller and taller every way because the crust has nowhere to go but up. So some examples of this type of folded mountain formation would be the Himalaya Mountains. Now, if you have a continental oceanic plate colliding or converging, the crustal formations you can get are volcanic mountains on the continent and trenches in the ocean. So what you have here is the oceanic plate, which is more dense, more heavy, subducts. It ducks underneath that continental plate, melts in the mantle, and then magma is pushed up, forming these volcanoes or volcanic mountains. And where that subduction takes place is where you're going to get the trenches, which are deep depressions on the bottom of the ocean floor. An example of one of those trenches is the Mariana Trench. Here it's one of the deepest depressions in the ocean due to subduction of that oceanic plate. And then this is kind of like a map view of what the Mariana Trench would look like. Now, if we have an oceanic plate converging, colliding, or coming together, what we get for crustal formations are volcanic island arcs, trenches, or volcanoes. So here what you have is the older oceanic plate, which is more dense, is going to subduct underneath the younger oceanic plate. And then that oceanic plate is going to melt in the mantle and push magma up, forming these volcanoes or volcanic islands, forming an arc in the middle of the ocean. One example would be the Aleutian Islands up in Alaska. Now, at all boundaries, earthquakes are happening. That's going to happen because you have motion there, movement. Earthquakes are not a crustal formation, but more of an occurrence that's going to happen at all of these plate boundaries. And then lastly, divergent boundaries. This is a boundary between two tectonic plates that are moving away from each other. The crustal formation depends on the type of plates that are diverging. So the direction of the plate movement, moving away or dividing, and if it's a continental plate dividing, so if it's land and land moving away from each other, you can get a rift valley, okay, or you can get volcanoes. So here an example would be the Great Rift Valley in Africa, where you have part of the continent of Africa moving away from the other part. If you have an oceanic plate diverging or dividing, the crustal formation you can get is called a mid-ocean ridge. You can get volcanoes, and the process that happens here is on the ocean floor, you have one part of the ocean moving away from the other part, so magma is coming up, forming these volcanoes. We call this seafloor spreading, because what you're getting is new crust. In fact, it's the newest crust on Earth, so it's the newest land forming on that ocean floor. So an example would be the mid-Atlantic ridge in the Atlantic Ocean. So here's North America. You can see Iceland up here. Iceland, in fact, is diverging as well because it's on this divergent boundary. There's lots of volcanic activity also happening here, as well as new crust. Okay, and this picture, this would be your mid-Atlantic ridge. It's kind of just showing you those underwater mountains underneath the ocean or underwater volcanoes, all new crust. And then transform boundary. Transform boundary is between two tectonic plates that are sliding past each other in opposite directions. So the crustal features formed would be a fault, okay, and faults happen from the stress of shearing, which can cause earthquakes. So a lot of times the transform boundary is associated with earthquakes. The San Andreas Fault in California is an example of a transform boundary, and you can see here what you have is the Pacific plate sliding past the North American plate, and California is on this transform boundary. That's why we're familiar with California having lots of earthquakes. From a satellite view, this is what the San Andreas Fault looks like, and here's another picture as well. All right, I would like to go over some former STAR test questions on the concepts we just covered. You'll also have a Schoology assignment where the same questions are asked. So, folded mountains in this model form which type of plate boundary? So here you have a continental crust and a continental crust converging, colliding, and what you're getting are these folded mountains. Okay, and again, the elevation just keeps increasing on these mountains. So we know that this would be a convergent boundary where plates are coming together. The thick black lines on the map show the locations of mid-ocean ridges. So all along here we have mid-ocean ridges. What geological feature is most likely to form at a mid-ocean ridge? So at a mid-ocean ridge, we are on a divergent boundary where you have oceanic plates diverging from one another. They're dividing. So here's a little image I put in. So you have one oceanic plate moving away from the other oceanic plate. Magma comes up. Remember, this process is called seafloor spreading, where you're getting the new crust on Earth. But what we get here are volcanoes, underwater mountains. So your answer would be volcanoes. That's the best choice here. Note too, we never discussed these other geological features. Arrows indicate the movement of the plates. what plate boundary is shown. So looking at the arrows in this satellite image, you understand they are sliding past each other. So this would be a transform boundary, like the San Andreas Fault in California. So we're on a transform boundary, and the crustal formation would be a fault. The Aleutian Trench is an underwater feature near Alaska formed by the movement of two tectonic plates. What additional geological feature often occurs along this plate boundary? So this is a nice image because it's showing you with arrows. It's a convergent boundary where two plates are coming together or colliding. And it's telling you it's the Pacific plate converging with the North America plate. So what you have here is the oceanic plate subducting underneath this continental plate, and you're going to get these trenches, underwater trenches, deep depression. But also the other geological feature would be volcanic islands, like the Aleutian Islands, which are they form an arc as well, and they're called volcanic island arcs. So B would be your best choice. We get these trenches underneath the water, and we also get these volcanic island arcs popping out of the water because that oceanic plate subducts, melts, and pushes magma up, forming these geological features. Okay, this year we also studied topography and satellite views. So topography is a type of map that represents elevation on Earth in a 2D format. So when you're looking at these contour lines are going to be representing elevation. So when you have these contour lines that are far apart from one another, we say that the elevation is gradual, meaning that it's not steep. Okay, but when the contour lines are close together, it means that the elevation on the map is very steep. So if we were to look at a mountain or a crustal formation on Earth, we can look at the contour lines to understand the elevation. Is it gradual or steep? So this is an example of a topographic map, and a closed contour line is the same elevation all the way around it. Okay, so this line, this circle here, this closed contour loop would represent the same elevation. The smallest contour loop on a topographic map represents the top of the hill or the mountain. You always want to look and see what your contour intervals are. That's what the elevation goes by. So if you understand this closed loop is the top, you can count your intervals and understand the elevation of the hill. Okay, so the question reads, what is the change in elevation for the hiker that took the steep path? So first you have to know which hiker took the steeper path. And if we look here, these contour lines are far apart. So hiker B would have the gradual slope, and hiker A would have the steeper slope because these contour lines are closest together. Here the contour, these are very close, so this would be the steepest side, but our hiker is here. So we only want to look at hiker A because hiker A is at the steep side of the hill. So now let's understand what elevation hiker A is on and where hiker A has to go. So if they tell you that this contour loop is 600 feet and we're increasing to the top, we can understand that this elevation here where hiker B is at would be 580 feet. So if we follow that around here, this would be 580. So hiker A would be at an elevation of 560 feet. So if they're at 560 and they want to go to the top, we count by 20s. So 560, 580, 600, 620, 640, 660 would be the top of the mountain. And remember, this elevation, 660 feet, is the elevation all the way around. Okay, so if you want to know the change in elevation for the hiker, you have to take 660, subtract the elevation that the hiker is on, and we said the hiker was on 560. So 660 subtract 560 would be 100. And if we were to grid that, we would put 100 for 100. And here's your decimal point. You can put in your zeros, and then you would have to bubble that in completely on your test. And then lastly, we studied satellite images. We use satellite images, which are photos taken from space, to study these crustal features or geological features on Earth and how they might change over time due to weathering, erosion, and deposition. Okay, so I'm going to read to you below about these satellite images, and then we're going to make an inference based on them. So here is a satellite image from 2012 and then 2013, and this area is being highlighted here. So let's read. It says the satellite images show evidence of deforestation near the Amazon River in Peru. When trees and other vegetations are removed from the rainforest, the plants no longer protect the soil. How is the process of erosion most likely affected by deforestation in this area? So first you would need to understand that what you're looking at. So here you would understand this is the Amazon River, and before you have the same view here, but what happened was that people took down the forest. They clear cut by chopping down trees, taking away the vegetation, and we understand that vegetation, trees, their roots hold down soil in the ground. So if they cut away an area, what happens is that this area is now vulnerable. So this soil is no longer in place by the roots of plants and other vegetation. So this soil now could get washed away and it can go into the Amazon River. Okay, so erosion is going to increase. So this area could increase and grow larger. So when vegetation is removed, soil is exposed and the rate of erosion increases. Soil and other sediment may be moved by wind or washed into the river by rainwater. Okay, so I hope that was helpful, and that was our review. Stay tuned for tomorrow's review as well.